Okay, in this examples, we're going to look at the polynomial schemes, and this data is from advert.xlsx file. So we have data for 22 weeks, and we have amount spent on advertising, the type of advertising that we did during that week. Okay, and there are 3 types of advertising, and then what the actual sales was for that week. So right now we want to predict sales based on the advertising that we have, advertising budget, the amount spent on advertising. Therefore, let's first define the y variable and the x variable. So y is sales. Okay, we can say weekly sales, and x is advertising. So let's develop a scatter plot, okay, for sales in the x-axis and advertising amount spent on advertising in the x-axis. So let's highlight that and go to scatter plot. Okay, and then you add the x-axis values here, P12 through P33. Okay, so that's our scatter plot. So we have N12 through N33 on the y-axis and P12 through P33 on the x-axis, and we can see, we need to format this a little bit. So sales versus advertising, advertising on the x-axis, sales on the y-axis, and you can very clearly see a non-linear pattern like that. So let's look at both models, fitting a straight line or fitting a quadratic equation that has a non-linear shape. So what are the 2 models that we're going to look at? So linear function, and then this is the quadratic function. So linear function, no problem, we can set up the linearest function, 1 column for the slope and 1 for the intercept, and then we can do linest. Now sales is your y range, comma, amount spent on advertising, that's our x range, comma, comma 1, close parenthesis, control shift enter. So that will give us the model. Let's do a little bit of formatting. Okay, there you go. So that's our model number 1. Okay, now model number 2, we're going to include the square term. So all we have to do is, so this is x and this is x squared. So all we have to do is to simply take the x value from each row and square it, and use that column as another x. So go, that's the x value for the first row, and then you square that. Copy that. Okay, so now we have a column of x and a column of x squared. So we just go ahead and run regression. You can do data regression or we can do linest. Now we need 1 column for x, 1 column for x squared, and then 1 for y-intercept. Okay, so then let's do linest. Now this time now let's do nest. Now y range is the same as before, comma, now the x range is that, comma, 1. Okay. So that's the nonlinear quadratic function. As you see, we didn't have to do any transformation or anything. All you have to do is to set up the necessary column, squared column, cubed column. If you want a third degree polynomial, then you have a cubed column. Or if you have more than one x, then you can do a cross or interaction term, multiply one with the other. Okay. So all kinds of nonlinearity can be incorporated, but you have to be very careful. You shouldn't just do all kinds of. You have to be careful not to have too many of these calculated columns, because if you have too many of these calculated columns, your model will become very unreliable. Even though you may artificially be able to get very, very good fit outside of your data, the fit may be of not much use. So here r squared for model 1 and r squared for model 2. So you see the fit is definitely much better for the second model. The standard error, okay, for the first model and the standard error for second model, and definitely standard error for the second model. I'm sorry, standard error. Okay, standard error for the second model. Okay, so definitely much better. Now f value, there is the f value, and the f value here is that one, and the p value is f dot dis dot rt of that f, comma, the degrees of freedom for the first model, the numerator degrees of freedom is 1. There is only one x variable, and the degrees of freedom for SSE is there for the first model. Okay, for the second one is, that's the f. Now 2 degrees of freedom, because you have 2 independent variables, x and x squared, and that's our SSE degrees of freedom. So p value is close to 0. So both models are significant, but model 2 is much better because r squared is large and standard error is small. So this is the first category of nonlinear function that can be, we can do regression as for a nonlinear function. Okay. Now remember, I'm not going to go over an example for 2 variables where you have interaction terms x sub 1 times x sub 2, and this is easy enough for you to do. All you have to do is to set up additional columns as necessary and then run the regression for all those columns that you have set up. Okay. Now let's in the next video we'll look at the second category of nonlinear functions, where the function will have to be transformed into what appears to be a linear function.